Good morning, students. Today you will be asked to practice one problem from Gauss theorem. But before going to that, let us just have a revision on the notes that you have written. Okay, what is Gauss theorem? First of all, it is a second generalization of Green's theorem. Okay, if we have S to be any closed surface enclosing a three-dimensional region E. Remember, here we have S and E. And if f, g, and h are three functions of three variables, and each of which is continuous and possesses continuous first order partial derivatives f of x, g of y, h of z, it means you you differentiate f with respect to x, t with respect to y, and h with respect to z. At each point of E and S, then in Gauss theorem you have triple integral with respect triple integral over E of f of x plus g of y plus h of z with respect to dx dy dz equal to the double integral over S f dy dz plus g dz dx plus h dx dy, where the surface integral on the right is taken over the exterior of the surface S. Remember, it's taken only on the exterior of the surface S. In Gauss theorem, we're trying to relate the triple integral or the volume integral. Here E is the volume and the double integral over S, where S is the surface. Now if I explain you with an example, suppose if you have a cube, sorry, let me draw a cuboid for you. Here you have 6 surfaces. At the top, at the bottom, then to the right, to the left, then at the back, and this one in front. So you have 6 surfaces. It means that this S you learn from an example. This S you are going to find out 6 surfaces, but the volume E, this region E enclosing by these surfaces will be only the interior, only that volume inside which is enclosed by these 6 surfaces of this cuboid. Why we are trying to relate this region E with this surface S, because sometimes it's quite difficult to calculate the integral using E, or sometimes it's quite difficult to calculate the integral using S. Okay, as find out from the first example. In the first example, we are trying to evaluate the surface integral. Okay, this is the surface integral. Okay, S with the help of Gauss theorem over the sphere. Here, S is the sphere, which is the surface of the sphere. X square plus y square plus z square is equal to A. Now, if I draw a sphere, okay, this is a sphere. Okay, let me draw. Okay, at the center. Okay, this is a sphere. And the radius of this sphere is A. Similarly, from here to here is A. A. What is S? S is the exterior surface of this sphere. Okay, if you find out using S, then you have to find using out the exterior surface of this sphere, which is represented by this equation. Now, if you bring out from the surface of a sphere to the volume or the region E, which is enclosed by this surface, you will get the volume of a sphere. Okay, have a look at the calculation. By Gauss theorem, you have this integration over E is equal to this double integration over the surface S. Here you have F, here you have G, and here you have H. Okay, since all F, G, and H, they have the partial derivative with respect to X, Y, and Z exist, so we can use Gauss theorem. So what we're going to do is we bring from the surface to the volume E. In our calculation here, in the volume E, we're trying to bring it to the for this E here, we are trying to bring it to the polar coordinates. Okay, the polar coordinates for the sphere is x equal to r cos phi sin theta, y equal to r sin phi sin theta, and z is equal to r cos theta. And where the value of phi ranges over from 0 to 2 pi, the value of theta from 0 to pi, and the value of r from 0 to a. Remember, if it is only the surface, then the value of a is fixed. That radius, okay, the value of r is fixed. It will only be r equal to a. But for the volume, it starts from, the radius starts from 0 to a. Okay, as in this example, the radius will start from here, then it keeps on increasing, then it goes till the radius r is equal to a. Since we are changing it to the polar coordinates, then we have to find out the Jacobian. After all the calculation, we will get this value here, r square sine theta, is our Jacobian. Therefore, the integral is becoming 3. If we have done the calculation, 3 then over e r square sine theta dr d theta d phi. Okay. Remember, phi is ranging from 0 to 2 pi, theta is ranging from 0 to pi, and r from 0 to e. If you do the calculation, then we'll get the answer to be equal to 12 pi a to the power 5 by 5. Similarly, for the second example, which is, okay, let me read the question. Evaluate this double integration over s of x squared dy dz plus y squared dz dx plus 2 into xy minus x minus y into z dx dy, where s is the surface of the cube. Okay, that surface of the cube. Let me draw. Okay, let me use this cube before. Okay, suppose this is the origin O. X will vary from 0 to 1 here. Y will vary from 0 to 1. From 0 to this value here equal y equal to 1. Similarly, z will vary from 0 to this value here, which is equal to 1. Here you know the value of f, g, and h, and the partial derivative of f with respect to x, of g with respect to y, and of h with respect to z, they exist, and f, g, and h are all continuous. So you can use Gauss theorem for finding out this integration. Therefore, if you use Gauss theorem and do all the calculation, you will get the answer. And in this third problem, here we have to verify Gauss theorem for the surface integral. Okay, this integral where S is a surface bounded by the rectangular parallelepiped. Okay, the value of x ranges from 0 to a, of y from 0 to b, and of z it ranges from 0 to c. Here we have to verify. It means that we have to find out volume integral separately, and then we have to find out the surface integral separately, and we have to check if the two integrals, if we get the same answer or not. Okay, since we have to verify, we should get the same answer and it will be verified. So here we first find out the volume integral. I will not show you everything. Here from the question we have f equal to x square minus yz, g equal to y square minus zx, and h is equal to z square minus xy. You find out the partial derivative with respect to x, for g with respect to y, and for h with respect to z. Then you find out the volume integral using Gauss theorem. Okay, you have this as a formula. Okay, where E is the rectangular parallelepiped given by this one. Remember, E is the volume inside that enclosed by the surfaces of this rectangular parallelepiped. For the volume integral, if you have done the calculation, then you'll get equal to ABC into A plus B plus C. Next, we have to find out the surface integral. The surface integral. Okay, if we draw this rectangular parallelepiped, we name this vertices, this at the center here, so at the origin here as O. Okay, then A, B, C, D, E, F, G, and so on. For the surface integral, remember, okay, it will be the same picture as here. For surface integral, remember, we have to find out the integration of the surface over the surface separately. It means that we have 6 integrals, I1, I2, I3, I4, I5, and I6. We have 6. Since we have 6 surfaces, then we have to add them together to get the surface integral. Okay, the first surface at the top, then the bottom, at the back, in front, to the right of this, and to the left, and we get a total of 6 surfaces. Here, that is why we're using Gauss theorem. Since if we find out the volume integral, we are finding out only once, since we have only one volume of this rectangular parallelepiped. But if we have to find out the surface integral, then we have to find out 6 integrals, since we have 6 surfaces of this rectangular parallelepiped. Okay, try to do all the calculation, then you'll if you add them together, you will get the same answer as that of the volume integral. This is what we have got from the surface integral, and it is equal to the volume integral. Now, you'll have to practice this same example, except we change the value of x Okay, let us change the value of x from 0 to, okay, let us write 2, from 0 to 3, and from 0 to 4. Okay, for you to practice, you have to find out, you have to verify Gauss theorem for the surface integral. Okay, this integral you have to find out where S is the surface bounded by the rectangular parallelepiped. Okay, you don't have to go for this A, B, and C, but you have to go by the rectangular parallelepiped. X from 0 to 2, Y from 0 to 3, and Z from 0 to 4.